Okay, so here we go. Let's go over some of these problems. Let's start with number 7 here. It says how many moles of copper will be deposited from a copper sulfate solution by a current of 12 amps flowing for 8 hours. Okay, so what an amp is actually 12 amps is equal to 12 coulombs per second. That's basically what it's saying. You're having that many coulombs per second. All right, now we want to know how many coulombs are going to flow through total. So we have to multiply this coulombs per second by the number of seconds. Okay, but it's given it to us in 8 hours. So we're going to multiply the 8 hours. So 8 hours, we're going to convert that to seconds. So we're going to multiply by 8 hours, but we want to get rid of that hours. So it's 1 hour is for every 3,600 seconds. You could go to minutes first if you want, but I just know this conversion already. So it's 3,600 seconds per hour. So again, coulombs per second. That's what amps are. So 12 coulombs per second. Then we'll get the number of coulombs. We also know that 1 mole of electrons requires 96,500 coulombs. Okay, so if you want to move or want to deposit 1 mole of electrons, you need 96,500 coulombs. Okay, so now you'll get number of moles of electrons. Okay, and then the last thing here is we don't want moles of electrons. We're looking for moles of copper, right? Moles of copper. So we do know that copper, the Cu is Cu2 plus. So we know there's actually 2 electrons for every 1 mole of copper. So 2 electrons for every 1 mole of copper. Okay, this is kind of like a stoichiometry problem here. That's basically what it is here. We'll see all the units cancel out. So seconds cancels with seconds, hours with hours, coulombs with coulombs, moles of electrons with moles of electrons. And then we'll wind up with moles of copper, really copper 2 plus, but really copper in general, it's just copper. So you get 4.03 moles here. Oh, and I forgot. What did I forget here? Oh, no. Originally, when I did this problem, I remember I wrote 18 here, and that's why I got 4.03. I wrote 18, but it's 8, and you get 1.8 moles. I'm looking at my work here that I did on the other paper, and it says 4.03, but then I remembered I originally wrote 18 here, and that was wrong, and I don't know why I did that, but anyway, so you get 1.8 moles of copper, which is answer C. Okay, this is pretty standard, this whole process here. It's not necessarily a formula, but you take the amps times the time, and this is got to be in seconds, times in seconds, times 1 over Faraday's constant, times the number of moles of element over the number of moles of electron. We did this in the Faraday Poggle. You can find this kind of work in the Faraday Poggle that we did. It's towards the end of it. This whole formula comes at the end of the Faraday Poggle if you're interested in where that is. Okay. Okay, next thing, this one's actually really simple. It's actually pretty easy. I was like confused at first, and I was like, oh wait, that's super stupid simple. Okay, so it says 2 kilometers, one containing silver nitrate solution, the other of an unknown metal has a 2 plus charge, are connected in series. So basically the same amount of current is going to be running through them. So 4 amp, because in series they're going to have the same current, right? The current won't change as they run through series. Okay. After 4 amps of current is passed through the coulometer, 11 grams of silver and 6.05 grams of M are deposited. What is M? You actually don't need to know this. You don't need to know this. Well, I guess you can know that. You have to know that silver is +1, so you're only having 1 mole of electrons. for each silver, whereas the M is a +2, so you're having 2 moles of electrons. So you do need to know that. But first of all, I want to find out how many moles of silver this is. So I'm going to take the 11 grams of silver and convert it to moles. So 1 mole is 108 grams, and I get 0.102 moles. Okay, and we know that I'm going to create double the amount of silver that I will M metal, because this requires 2 electrons, where this only requires 1. So I'm going to divide this by 2, and I'm going to get 0.051 moles of M. So I know that I will create this is the number of moles of the metal that will be deposited. Okay, so that's the number of moles that will be deposited. And I already know the grams, so we can find the molar mass of this metal by just taking the grams divided by moles. So you take the 6.05 grams divided by 0.051 moles, and you'll get the molar mass to be roughly about 119 grams per mole. And then you look and find which one of these metals is closest to this molar mass, and it comes out to 10 Sm. Okay. Next one, the equilibrium constants. So this one I got a bunch of questions on. So here, I know because we really didn't go over too much of this equilibrium constant stuff, but really you just got to kind of know the formula for this. And one of the tricky parts of this one that really screwed me up was that they made this is actually going to be negative, the overall cell potential. I just flipped them to make it positive, but that was stupid of me. So anyway, we keep the bottom one, and then we flip this one to get the E cell. So E naught of the cell is equal to, I got negative 0.28. Okay, and then we're going to use this formula. The formula is that well, there's actually 2 formulas we're going to use. First of all, that delta G equals negative. Actually, you know what? There's an easier way to do this. Yeah, I'm not going to use that one. I'm going to use the one-stepper. Okay, so this is we're going to assume, yeah, we're going to figure this out. So we're going to do E naught of the cell equals 0.0592 over n times log of k. Okay, the E naught of the cell is 0.28. Okay. This is that, 0.0592. And n is the number of electrons, and this is just 1 electron. And then we're finding log of k. So we're just going to solve for k here. And when we do that work, so you're going to do negative 0.28 divided by 0.0592, and then 10 to that power. And that will give you k, because that's the opposite of log. So 10 to the power of 0.28 divided by 0.0592. Okay, and we get 1.9 times 10 to the negative 5th, which is closest to B here. So there's another way to do this, and I actually did it the other way, but that takes 2 steps. This is just the easiest way. This equation right here is a good equation to memorize and know. I'm not sure if they give it to you on the reference sheets, but it really helps. It makes it a lot easier. Okay. You could have found delta G first and then use delta G to find the equilibrium constant, but I think that's the easiest way to do it using that formula. Okay, so this one, what is delta G for the reaction given there? So for this one, first of all, we're going to use this delta G equals negative NFE, where N is the number of moles of electrons. This is Faraday's constant, or 96,500, and E is E naught of the cell. So it's really, this one's pretty simple too, as long as you can find E naught of the cell. Okay, and then this one's a little bit tricky because you just gotta just look at what this equation is and how these are arranged. So H2O, this one we keep, and then K, we flip this one. So we have 2.92 minus 0.83, and we get 2.09. So that's the E naught of the cell. Okay, the moles of electrons, so in this case, there's going to be 2 electrons, so negative 2 times 96,500 times E naught, or 2.09. Okay, when you do all this work, you should get negative 403.37 kilojoules. The answer, actually, when you do all this, you'll get it in joules. But then you have to convert it to kilojoules by dividing by 1,000. Okay, so yeah. So if you got an answer that was really, really big and you're like, where is that? It will divide it by 1,000 to get kilojoules. So when you do this, then divide by 1,000. Okay, really, well, oh yeah, and the answer is A, negative 403. Okay, number 25. So for this one, again, you got to find, you're using the same formula that we did before, delta G equals negative NFE. So mg, this one we flipped. So the overall cell potential will be 2.37. So you have 2 electrons. So negative 2 times F, 96,500, times E, 2.37. And then divide that by 1,000 to get it in kilojoules, because that's what the answer, they tell you to get the answer in. And you actually get negative 457.4, but this is the closest answer, A. A is the closest answer there. Okay, and then 26, pretty much the same thing as the other ones. Delta G equals negative NFE. I think I don't remember which one of these. Some of these I mixed up these things. So make sure you go back and check. I think I wrote the wrong ones for some. I don't remember which ones, but I fixed it now, so they're good now. But they might have been wrong before. Okay, but 26. So here, so this one we have to flip it, flippity flip. We leave that one, so it's actually negative 0.77 plus negative 1.18, and we get negative 1.95. Plug it into that delta G equals negative NFE, where N in this case is 2, all that good stuff. And when you do all the work, you get D as your answer. Don't forget to divide by 1,000, because the answer is going to be given in joules. This is going to be in joules, and then divide by 1,000 to get kilojoules. Okay. Number 27. This is the one. Number 27, I wrote for Cu2 plus rather than Cu plus. Where is it? There it is. Yeah, so originally I had the wrong one here. I had this wrong one here. So if you got the wrong answer because of that, then you just had to change this one. But same thing, what's the standard cell potential for this? This one's really, really simple, trying to find the cell potential. So you got to flip this one. And so that becomes negative. So it's 1.36 plus negative 0.52. And you'll get 0.84, which is that one right there. And before, I think I wrote the wrong one. That's why I got D. And then so just make sure you're paying attention to that. It's a +1, not a +2. I wrote the +2 one in there before. Okay, number 28. What is the standard cell potential here? I also wrote the wrong one for this one. Or I copy and pasted the wrong one for this one. This one was wrong. This is negative 0.35. Okay, that one you keep. You have to flip this one, so that becomes positive 0.83. Then you combine these two together, so negative 0.35 and 0.83, and you should get I got 0.48, positive 0.48. Closest to that one is that one. Closest one is that one. Okay, next one. What's the standard potential for this one? So PB2 plus, that we keep. But we have to flip this one. When we flip it, it becomes negative. So negative 0.77, negative 0.13. Add them together, you get negative 0.9, which is A. Okay, number 30 requires a little bit of an explanation here. So which of the following will Br2 react spontaneously? So spontaneously, in order for it to react spontaneously, E naught of the cell has to be positive for a spontaneous reaction. So just remember that E naught of the cell has to be positive. So we're looking for, when we combine the two to get a reaction, we get a positive E cell. Okay, one has to be oxidized and one has to be reduced. So Br2 is being reduced right here. So it's being reduced. So we need something that's going to be oxidized. Okay, so to do this one, to make Pb oxidized, we have to flip it. Okay, and that would be positive 0.126. So that would make positive 0.126 and 1.06. That would make this positive, and that would be the one that's spontaneous. Just so happened that that was the first one I looked at. We could look at the other ones too. Cl2, we'd have to flip this one, and that would make it negative. Okay, if it becomes negative, negative 1.36 and 1.06 is negative 0.3, so that one can't be it. I2 wouldn't even work because I2 and Br2 both want to be reduced, so it won't even do that at all. And then F minus, if you flip this one, it becomes negative, and that becomes negative, so that one doesn't work either. Okay. 31. Which of the following will most easily oxidize? So we're looking for something that's going to be oxidized. So basically, you flip these, right? So this one, F2 wants to be reduced. It won't be oxidized. So we can automatically get rid of that. Same thing with H+. H+ won't be oxidized. It will be reduced, so we can get rid of that one, but it's not there. But it's also 0. F minus will be, if you do it the opposite way, if we want it to be oxidized, that means it loses electrons. That would be negative 2.87. Okay. Lithium plus, we'd have to flip it. This would be, in order to be reduced, it requires this much energy. So that would be the opposite. That one wouldn't even happen. So it's got to be E. 31 is E. So you flip this one, that becomes 3.04, and that reaction is Li to Li plus E minus. That's positive. That means it's spontaneous, and it happens very easily. Okay. If all of them were negative, we could say H2, but it's not, so that one's spontaneous. Okay, next one, 32. Whew. 30. Oh yeah, I forgot. 32 I crossed out. 32 is not on the AP exam anymore. I missed that one, so don't just ignore 32. I totally forgot to get rid of that one. Don't worry about 32. Get rid of it. Okay. 35. We're looking for the E. We're looking for the E naught of this reaction given the equilibrium constant, and E naught is equal to 0.0592 over 2 times the log of K, which is the equilibrium constant. So we're given the constant, so that's really easy. So 0.0592 over 2 times log of 2.2 times 10 to the negative 6. Do this math right here, and you should get the letter D. The letter D there. Okay, it's actually the same thing for this one. You're just plugging that in right there. And when you plug it in, you get C. You get C there. Okay, this one, 37 and 38, they're looking for the equilibrium constants given the E naught, or you have to find the E naught first. So we find the E naught first. So first of all, PB2 plus is on this side, so we keep it. We got to flip this one. Oop, flip. So that becomes negative. So it's negative 0.34 plus negative 0.13. And I got negative 0.47. That's the E naught of the cell. And we know that is equal to 0.0592 over 2 times log of K. So we're going to solve for K. So K is equal to 2 times 0.47, and this negative, divided by 0.0592, and then 10 to that power. And when you do all this little math thing over here, you get 1.32 times 10 to the negative 16. And that is closest to answer E. Okay. Same thing for 38. Same thing for 38. Okay. So here we have this. We got to flip this one. Flip, Philadelphia. And then add it to 1.07, we get 0.3. So 0.3 equals 0.0592 over the number of electrons that are exchanged. The number of electrons are 2. And then log of K. And again, we're solving for K. So 0.3 times 2 divided by 0.0592. And then in order to solve for K, we do 10 to that power. And we get 1.37 times 10 to the 10th, which is closest to answer C. I don't know why they got 7. I don't know if I screwed something up somewhere or wrote a wrong number, but this is what I got. I couldn't figure out what I did wrong or if the answer was wrong. So if anyone knows what I did wrong or where I made a mistake, let me know. But otherwise, that's as close as I'm going to get to it right now. Okay. I don't know if I missed something. It's 2 electrons. Yeah, 2 electrons. Yeah. I don't know. I do not know. So anyway, if you can tell me what I did wrong, let me know. Otherwise, that's it. If you have any other questions about anything else, please do let me know. Otherwise, that is all.